Hi, I'm Adam Hopkins. I am the marketing chair for the Society for Applied Spectroscopy, and I have with me today Dr. Joseph Razzell Hollis of the NASA Jet Propulsion Laboratory, and we're going to be talking today about his involvement in the Perseverance Mars rover project and a little bit about how it is that he got here, because it's the kind of thing and the kind of place that few spectroscopists get to go. So thank you, Joe, or Joseph, for being here with me today.
It's awesome to be here.
So right off the bat, let me just ask you to briefly describe your involvement with the Perseverance rover project.
Okay, yeah, so I am a postdoctoral scientist at the Jet Propulsion Laboratory. I'm specifically working on Sherlock, which is one of the spectrometers on board the rover. I've been at JPL for just over 3 years now, so I've had the opportunity to be involved in the project kind of sort of at the finalization stage, right? So it was when they were sort of putting together the last parts of the rover, assembling the whole thing, shipping it off to the launch site, and then, of course, launching it and landing it. And now my job primarily focuses on getting ready to interpret the data that we're going to be getting back very shortly.
Cool. So final stages is when you started getting involved, and now it's going to be data analysis. So what the Sherlock, I think it's the scanning habitable environments with Raman and luminescence for organics and chemicals. Is that
Right.
Hey, all right. Uh, um, so can you just tell me a little bit about what exactly the Sherlock is?
Yes, of course. So Sherlock is the arm-mounted deep ultraviolet Raman and fluorescence spectrometer. So it's one of the boxes that's attached to the very end of the robotic arm. The instrument itself is about the size of a cereal box. It incorporates the UV Raman fluorescence spectrometer, but it also has an attached camera called Watson, which is it's the camera that's responsible for taking, for example, the selfies. They just released one the other day. It was the first official selfie of the entire rover, and the way they take that is, they extend the robotic arm and then they rotate the arm so that the camera can capture a picture of every part of the rover, and then they stitch those all together. But Sherlock itself, the spectrometer, is an imaging spectrometer. It's mounted to the arm so that we can extend it over and position the instrument over a rock of interest. So let's say that we're driving around Mars, Jezero crater, we find a rock that's particularly interesting. The way we'll try to analyze what's there is we'll cut away some of the surface material using the drill just to expose like a fresh surface, probably like half a centimeter to a centimeter below the original surface. And then that fresh surface will hopefully have any like intact material that was left behind when the river and lake system that used to exist in Jezero dried up. We'll then shoot that rock with our UV laser that's part of the instrument, and we'll scan it across the rock surface, kind of like in a raster path, and we'll look at the light that comes back from the rock. So we're collecting Raman and fluorescence at the same time. So if you're not aware, Raman scattering is this phenomenon where you shoot a molecule with a very monochromatic light source. Some of that light gets scattered inelastically, so it comes back with a different energy to what you put in. And the change in energy corresponds to the excitation of particular kinds of vibrations in the molecule itself. So they occur at very specific energies. And if we look at those changes in energy, we see a pattern of peaks that correspond to the vibrational modes of a molecule. And it's extremely specific. It's actually sometimes referred to as the molecular fingerprint, because it's so specific to a molecule structure. So as we scan across the rock surface, we're looking for that Raman scattering, but we're also looking for fluorescence. Fluorescence is like the direct emission of light from molecules that have absorbed the laser light and re-emitted it. And it's a classic kind of thing. It's stuff like glows in the dark. That's a form of fluorescence. So what we're looking for is the fluorescence and Raman scattering of primarily of organic molecules. So the kind of molecules that could be the building blocks of life as we know it. We're looking for those kinds of signatures, and we're generating a spectral map of the surface that we're scanning so that we can kind of correlate the presence of any organic material to the presence of particular minerals or like bands in the geological structure, so that we can build this clearer understanding of when did those molecules get introduced to these rocks? What point in the geological history of Jezero crater did these molecules get trapped in these rocks and preserved over billions of years? Sherlock is actually extremely efficient. By virtue of we have quite a powerful laser, and so we don't need to fire as many laser pulses to acquire a certain amount of signal. So I would say that compared to some of the visible excitation Raman systems I've used, where it takes at least 30 seconds to acquire a spectrum, Sherlock could arguably acquire the same spectrum in about 10 seconds. So we're actually very fast. It's just that we're very conscious of the amount of time it takes and the energy.
Right. You mentioned energy here. Is that the energy that the rover has? Is there a fixed amount? I mean, it's got solar panels and stuff, right? Or
well, actually, it's a nuclear-powered rover. It has a radioisotope electric generator in the back, which provides a constant supply of power. Obviously, it's not a huge amount, and so the rover does spend a lot of its day charging its batteries, and then that energy is consumed whenever you do activities. So we never want to consume all the energy on the rover, because there are so many essential things like keeping the electronics warm and keeping the rover alive. Those things will always take priority. But certainly, I don't think Sherlock is is power hungry. We're fairly. I don't want to say anything specifically, but for us, it's just a case of there are so many things that the rover team want to do in a single Martian day. If we were to demand 12 hours of observation time, we will be upsetting a lot of other people who want to do their own measurements with their instruments. So it's a constant negotiation of who gets to do what and compromise. So thankfully, we're fairly time efficient. We can collect like a typical Sherlock survey of a sample in less than 30 minutes. I know that some of the other instruments take quite a bit longer than that to do comparable activities, but how quickly you get that information back depends on what other data products there are and the particular orbital passes, because the rover sends the information back by transmitting it to satellites orbiting Mars. So, for example, Odyssey or MRO, the European Trace Gas Orbiter is another one. Every time one of those passes over the rover, we have an opportunity to transmit a certain number of megabits back. And so unfortunately, on some days, you just can't get back as much as you'd like. And so you might end up having to wait, and you might not get your full data product back for multiple days. But generally speaking, it all does come back eventually. But from the data analysis point of view, the data gets downloaded, and within within an hour of it being downloaded, downlinked by satellite dishes on Earth, we're looking at the raw data and we're starting to make interpretations, because it might inform the decisions being made for what the rover is going to do the next day. So if we find a particularly exciting sample, one of the things we're concerned with is should we actually take that sample and cache it for eventual return to Earth? So do we use the drill and the corer on the rover's arm to extract some of that rock, put it in a sample tube, seal it, and then leave it behind for the future Mars sample return mission to pick up and bring back to Earth? So that's the kind of decision we have to make fairly quickly before we drive on to the next location. The reason why Jezero crater was selected as a landing site is because we can see from orbit that there is this beautiful river delta. So this kind of fan of mud and silica deposits that have been left behind when some ancient river entered the crater and there was a lake there. And when the water slowed down, it dropped all of the material it had carried from upriver, and they're just left behind this fan of sand and mud that has since dried out. Now, as far as we can tell, that lake and that river dried up, billions of years ago. So, those rocks had been deposited there a very, very, very long time ago. And one of the challenges on Mars is that if we're looking for these organic compounds that could have been the building blocks of life when Mars was potentially habitable billions of years ago, we have to look for what's left billions of years later. And as I said before, it's not a pleasant environment. So the real challenge is, how do you find where those molecules could be preserved? We know from studies on Earth that like certain kinds of rock, so like mudstones, are very, very good at trapping organic material. We would expect to find a lot of organic material in, for example, the deposits of that river delta in Jezero. But what will have survived over billions of years? How far below the surface do you have to get before you're safe from all that radiation that could be photolyzing and destroying those molecules? It's one of the challenges. It's part of the concern why we haven't seen very much organic material using other missions, is that until Perseverance and InSight, well, I suppose InSight landed first, but we've only really just scratched the surface of Mars, literally. Most of the previous missions would only remove like the top, the top centimeter or two of material. Perseverance is capable of digging at least 5 centimeters below the surface. So we're more hopeful that we'll be able to find some of that preserved material. We've picked what we think is a really good location that has lots of potential, and we've got the tools to look further below the surface than we ever have before. And we have these very sensitive techniques, such Sherlock is a in theory a non-destructive method of scanning a sample and in situ, and then you can so hopefully we'll be able to detect that material and then make the decision whether or not we want to store it in a sample tube and bring it back to Earth later for more detailed analysis.
Well, I want to thank you very much, Joseph, for taking the time to talk to me and and being interested in astrobiology and spectroscopy and doing something different. I bet you're certainly the first person I've ever met with that job title now. And so I thank you very much for the time, and look forward to reading your upcoming article in Applied Spectroscopy, and maybe I'll go back and look at the other one on beam propagation as well, just to get the full context. And I want to see this 3-line equation if it's in there. So thanks, and thank you for the work, and keep going and looking at what's out there.
Oh, well, thank you for having me. It's been an absolute pleasure.